About to do another linear programming NCA level 3 complete work through, this time to excellence on the Leo's Laundromat problem, which is about clothes dryers being either coin or token operated, how many to choose. And the first step in doing these is to choose your variables. You can read the sheet this time. I'm going to try doing it off this little whiteboard instead of working through it on paper. It might be a little bit nicer to read. So and you'll notice in the problem itself, it suggests that the objective function there, the income per month, which is what you would be trying to maximize, is written as 1000C plus 800T. So we're going to use those exact same variables. C was most likely the income from the coin-operated clothes dryers, and T is the token number of token-operated clothes dryers. So we'll use those things. Yep. And that helps us when we're trying to work out our actual constraints. So, to find the constraints themselves, we look through the information that we have about the clothes dryers, and we spot that here, space it is Laundromat for up to 40 clothes dryers. Note that the information prior to that, the $1,000 per month and $800 per month, contributed to the objective function, so we've already sucked up that information. We'll write it out a bit later on. Actually, let's write it down now I think about it. That comes to the objective function, so we'll call it that there. So, the space at Laundromat, up to 40 clothes dryers, and they both take up the same amount of space, coin and token operated. So how can we model that as a constraint? Let's think about that a bit. Well, we have basically the number 40 and some function there, number of each kind of clothes dryer. We could just add them together, and that is a up to 40 clothes dryers, so that means the number has to be less than or equal to 40, can't be larger. Okay, that's constraint number 1. The second constraint, it says the current demand means they must have twice as many token operated clothes dryers than coin operated. This one can be a little bit hard to get your head around, so I would do a little working before I write it out neatly here. There is a relationship between the number of the two, twice as many token operated. So the token operated are going to be twice as many as the number of clothes dryer ones. We've got to multiply the number of clothes dryers by 2 for the token operated ones, and then the question is which way around to put at least twice as many. So there could be more than twice as many, so T could be more than this number. So I'm going to put it that way there, around there. And now we actually need to rearrange this equation here so that it goes into the nice form for solving. We don't have to, but it's generally a good idea, especially if you want to use the calculator to solve it. So what we're going to do is simply move the t to the other side like that by subtracting it, and we're going to write that up here. And we check for some more constraints. We have the ongoing contract for the company making the tokens needs to have at least 10 token operated dryers. So that one's going to come as 10, at least 10, so 10 or more token operated dryers. And the dairy is not open 24 hours, so you just have at least 6 coin operated ones so people can get their coins. So at least 6 of these. I might put that nicely lined up under here, and you'll see what the reason for that is in a second. So there we have the problem laid out. Maximize income subject to these constraints here. Just these 4. I'm going to number them 1, 2, 3, 4. Like that, and that is our linear program that we're trying to solve. So I decided to draw these graphs quickly using Desmos instead of doing it by hand. I think you guys are good enough at that now. And there's only one real trick to it that's a bit different to what you did before. This line number 1 here, fairly straightforward from the 2 intercepts method, but this one here you may need to probably struggle with a little bit, because when you solve it either way you get both intercepts at 0, which is correct. It does in fact pass through 0, 0, but you can't find the other one up over here somewhere to draw the line. So what you actually have to do is put it into slope intercept form. So we're just going to do that. If t was actually a y value down here, this axis, then we want to put t on its own. So just rearranges to, and that's what that line there is. It's no intercept at all, plus 0. So the slope is 2 for 1, so it goes 0, and that's 5, 10, 10, 20, and so on. So for this one, need to be a bit more careful with the point test later on as well. So we have line 1 is this one here, line 2, that one I just described, which goes right through the origin, line 3, which is this one here, and line 4, which is the vertical one here like this. And you may notice that just here that these 2 points and also this one along here are not in the feasible region at all. So in actual fact we don't have to check anything to do with equation 3, because all of its intersection points are in the infeasible space. So that means we just have to find these 3 points here: the intersection of 4 and 2, the intersection of 1 and 2, and the intersection of 1 and 4. So let's do the easy ones first. So let's find the intersection of 4 and 2. We'll call this point A. And That's these two equations here. So we're just going to write them out. We can just substitute c equals 6 straight into the one above. So we've now got our two values. Which are 6 and 12. So our first critical point here is now let's look at the intersection of 4 and 1. We'll call this, that's 4 and 1, this one up here, which is the intersection of this and this. So we just copy them down. One is, and 4 is, whoops, that's C, sorry, C is equal to 6, so what am I doing? It's 40. So therefore, 40 minus 6. Giving us our 2 points again. So second critical point is at c equals 6. T equals 34. And the last critical point, slightly harder one, is the intersection of 1 and 2. You can use a calculator for it, of course. If you did use the calculator for it, you would enter the values like this. For 1, 1, 40, and 2, minus 1, 0. And solve it, but we're going to solve it by hand. So that's the intersection of 1 and 2. Just copy them down. This is a straightforward elimination. We can add the equations together and the two t's will cancel each other out. So we're going to get c plus 2c is 3c, plus t minus t is nothing, 40 plus 0 is 40. And therefore c is equal to 13 and a half, 13 and a third, sorry. And we can plug that back in, 13 and a third, into this one here. So t is equal to which comes to 26 and 2/3. Which gives us our third critical point here. So let's move on to calculating the objective. Recall that we made the objective function equal to P, or profit, is equal to 1000C plus 800T. That was actually just straight in the problem itself written out for us, and we've now found our 3 critical points. So we're going to test them all. This is the critical point. Just make sure I remember which way around they go. Next critical point is 6,34. And C is 13 1/3, 26 2/3. And we just put them straight into this. So that goes there, this goes there, that goes there, this goes there, and so on. So we get, still in green, so I've worked out a bunch of objective functions for these critical points here, and we can clearly see one of them is larger than the others, this one here. So our optimal solution is there. If you were to now write up that Leo's Laundry, they should buy 13 coin-operated machines and 26 token-operated machines, you'd probably get a merit mark for that. But to get a full excellence mark for this, you do actually have to check whether that really is true. The reason for that being that the exact objective point, kind of hard to see. Yeah, it is too hard to see. It lands in between a bunch of points right in there. So I'm going to draw a little blow up of what I'm seeing there. One line going this way, one line going this way, and a square around it like this. We have to check these 3 points here on the square, because this is the actual value we found, and we need to know whether or not the nearest points are in fact the best points. We rounded one up, this one, and we rounded this one down, so we ended up choosing this point here, slightly up and to the left, but we do need to check that this one here isn't more optimal. It's quite possible that it is in the diagram, and you might not be able to see this when you draw it out yourself. You might not be able to see that the other sides of that point around here are in fact in the infeasible space, so we don't actually have to check those ones right here, but but we need to check if those 2 points are in the feasible space. So let's check out those possible solutions. Note that in this case we can't actually use the solution because 13 1/3 coin operated dryers and 26 2/3 token operated do not make sense. You can't buy a third of a machine and hope it find it working. So we've got to search near the optimal solution, which I've drawn over here, which landed between 13 and 14 and between 26 and 27. That's the actual fractional optimal solution, and we have to check points near it to see if they are in fact actually both feasible, and then we have to check their optimality. And the 4 nearest points are obviously these 4 around it, that one, this one, this one, and this one. So you can find them by rounding them both down, rounding them both up. So both down, both up, rounding one down, the other up, and the other up and the other down. So let's list out what those points actually are. I'm going to start with these ones over here. So this point here, let's check its feasibility against these objectives. This is 1, 2, 3, 4 of my original constraints here. So does it satisfy 3 and 4? Yes, it obviously does. Those were all off to the side, but yes. So 14 is greater than 6, 26 is greater than 10, but C plus T here is 14 plus 26, which is exactly 40, which is less than or equal to 40. And the last thing to check is two C minus T is 28 minus 26 equals 2, and that is not less than 0, therefore not feasible. Which you can kind of see out there. The constraints actually go around here in this space here, but we've got to check it because graphical method isn't showing that very clearly. So let's check the next one out here, which is 1427. So 14 is greater than 6, 27 is greater than or equal to 10, but 14 plus 27 equals 41, which is not less than or equal to 40, So this one is infeasible. Alright, let's check this one down here, 1326. We've got 13 is greater than or equal to 6, 26 is greater than or equal to 10, 13 plus 27 equals 40, which is less than or equal to 40, and we've got 2 times 13 plus 26 equals 26, minus 26 equals 0, which is less than or equal to 0. So this one is feasible. This one here, last one. I've got 13 is greater than or equal to 6, 27 is greater than or equal to 10, 13 plus 27 equals 40, which is less than or equal to 40, and lastly 2 times 13 plus minus 27 equals -1, which is less than or equal to 0. So this is feasible. So both these 2 points here are feasible. So let us now check their optimality. Remembering that our profit function was $800T. So we're going to check this point here. And this one. And you should see that it's basically going to be 800 bigger, because the only thing that's different is that. We have now found an optimal solution. So our last part really is to write a nice statement at the end. Can we see that here? Yep. And if you can put all of that down, then you've earned yourself an excellence. And rather than doing that entire video all over again, I'll point out, of course, that the final number should have been 27 and not 26. I hope you all saw that. Cheers. Have a good one.